Hi everyone. In this video we'll go through two different types of matrices which are symmetric and skew symmetric matrices. We will also see how to express matrix as a sum of symmetric and skew symmetric matrix. Symmetric matrix. What is a symmetric matrix? If you take a transpose of a matrix and it will still be the same as original matrix itself, then it's called as a symmetric matrix. Say for example, take this matrix A is equal to 3, 1, 1, 5. If I take transpose of this, that is if I interchange the rows and columns, I will get the same matrix, which is nothing but the original matrix, right? The A transpose is same as the original matrix. That's why we call this matrix as symmetric matrix. This matrix A is called as a symmetric matrix. Skew symmetric matrix. What is a skew symmetric matrix? Small difference. Small difference is here A transpose is equal to minus of matrix A. In this case, in symmetric matrix, A transpose is equal to A. In skew symmetric, A transpose is equal to minus of matrix A. So let's take this example. Say this is matrix A. Now you take all of the columns, all of this first column, second column, third column, and represent it as rows. First row, second row, third row. That is, you find the transpose, interchange the rows and columns. Now you take minus as common factor, right? You take minus out. So what you will get? You will get a matrix. If you observe this matrix is nothing but matrix A itself. If you take minus outside. That is why in skew symmetric matrix, A transpose is same as minus of matrix A. Let's go through theorems and examples of symmetric and skew symmetric matrices. The first theorem states that if there is a square matrix A with real numbers, then A plus A transpose is a symmetric matrix and A minus A transpose is a skew symmetric matrix. Right? Let's prove this theorem. Let's assume that P is equal to A plus A transpose. So what we'll have to prove is when you add matrix A with its transpose, it should be a symmetric matrix, right? So what is the condition for symmetric matrix? Condition for symmetric matrix is A transpose is equal to A, right? Now, in addition to this rule, on the top of this rule, it is also stated that when you add matrix A with its transpose, then the resultant matrix is going to be a symmetric matrix. So let's prove this step by step. Let's assume that A plus A transpose is matrix B. Now what we will do, we'll transpose on both the sides. We'll transpose on both the sides, left hand side and right hand side. So we'll get B transpose is equal to A plus A transpose, the old transpose, right? We're going to apply transpose on both the sides. So now we'll write this as B transpose is equal to A transpose plus A transpose, the old transpose. This is based on the property of transpose of a matrix. What is the transpose property? If A plus B, the old transpose, is A transpose plus B transpose. So we'll apply this property here. So we'll get this. Now once we get this, we'll further simplify A transpose. What is A transpose of transpose? That is, there is a double transpose here. So there is another property which is A transpose of transpose is A itself. So we'll put this as A. Now B transpose is equal to A transpose plus A. What is A transpose plus A? We had assumed that A plus A transpose is B. So we can write this as B. So B transpose is B. Now what is the condition for symmetric matrix? Transpose of matrix should be same as the matrix itself. This is the condition for symmetric matrix, right? A transpose is equal to A. This is symmetric matrix, right? So now this condition is satisfied here. So therefore, we can say that B is a symmetric matrix. Now again, in turn, what is B? B is nothing but A plus A transpose. B is nothing but A plus A transpose. So which means, since B is a symmetric matrix, B is nothing but A plus A transpose. So this is a symmetric matrix. Symmetric. So A plus A transpose is a symmetric matrix. So we have proved that the first case we have proved that A plus A transpose is a symmetric matrix. Now similarly, we'll prove A minus A transpose is a skew symmetric matrix. So what we'll have to do? Similar steps. We'll assume C is equal to A minus A transpose, right? Now we'll apply transpose on both the sides, like the earlier theorem. We'll get C transpose is equal to A minus A transpose, the old transpose. Now using the property that A minus B, the old transpose is nothing but A transpose minus B transpose. This is the property. So we'll use this property here. So we'll get A transpose minus A transpose, the old transpose. Now what is the other property we have? Double transpose. A transpose of transpose is nothing but A itself. Now we'll use that property. So we'll get C transpose is A transpose minus A. Now we can just swap this, right? We can swap this and write as A minus A transpose. We can put minus common. If I take minus outside, then I can write it as A minus A transpose. It's the same thing. I can write this in this form, A minus A transpose, and put negative sign. So C transpose is minus of A minus A transpose. So C transpose is equal to, what is A minus A transpose? What we had assumed. A minus A transpose is C. So I can write this as minus C because this entire thing we had assumed as C, right? So now what did we get? C transpose is equal to minus C. This satisfies the condition of skew symmetric matrix. What does skew symmetric matrix say? Skew symmetric matrix says that A transpose is equal to minus of A, right? Here we have got C transpose is equal to minus of C, which means that C is skew symmetric. This confirms that C is a skew symmetric matrix. Now what is C? We had assumed C to be A minus A transpose, which is nothing but A minus A transpose is a skew symmetric matrix. As per the theorem, we'll have to prove that A minus A transpose is skew symmetric. So we proved here that A minus A transpose is skew symmetric. Both the cases are proved. Now let's go to the second theorem. Second theorem states that any square matrix A can be expressed as a sum of symmetric matrix and skew symmetric matrix. In the earlier theorem, we saw that symmetric matrix can be written as A plus A transpose and skew symmetric can be written as A minus A transpose. So now we can write a square matrix in such a way that we can represent it using sum of symmetric and skew symmetric matrix. Now only difference here is there is half here, right? There is a constant, there is a scalar here, right? So what we can do, similar to how we proved in theorem 1, we can prove here also. So we can assume that this entire thing is matrix B and this entire thing is, say, matrix C, exactly like the earlier one. We'll assume that matrix B is half into A plus A transpose. So we'll apply transpose on both the sides. We'll get half into A plus A transpose, the whole transpose. Now transpose of half is half itself, right? It doesn't matter for a real number or for any constant. So it will be half itself. And this is going to be A plus A transpose, the whole transpose. Now we can split this as A transpose plus A transpose and transpose, right? So now if we simplify this, it's going to be half A transpose plus A. This is equal to B transpose. Exactly like the earlier theorem, we got this. In the earlier theorem, we just had A transpose plus A. Here we have half in addition. We assume that half into A plus A transpose. We assume that this is B. So what is this? We can write this as B, right? So what did we get? B transpose is equal to B, which means B is a symmetric matrix. This is the condition for symmetric matrix, right? That B transpose is equal to B. Now what is B here? B in turn is half into A plus A transpose, which means this entire thing is a symmetric matrix. Same way, we can take C is equal to half into A minus A transpose. Now apply transpose on both the sides. You will get half into A minus A transpose, right? Following the same steps, finally you will get C transpose is equal to minus C. Only difference between theorem 1 and theorem 2 is that there is half here. So even though there is half here, still this entire thing is symmetric matrix and this entire thing is skew symmetric matrix. One more thing what we can do is we can multiply this. There is a property, right, where we can multiply. So half into A is half A plus half A transpose. We'll multiply this one also, half A into half A transpose. This is going to get cancelled and we're left with half A and half A, which is nothing but half plus half is A. That's why we can write square matrix A is equal to this entire expression, because ultimately when you calculate you're going to get A itself. Now let's take an example. Express this particular matrix B as a sum of symmetric and skew symmetric matrix. So we'll use a theorem. By theorem it states that we can write matrix A as half of symmetric matrix and skew symmetric matrix. We'll use the same logic here. So matrix B is half of B plus B transpose and half of B minus B transpose. We'll first calculate this, we'll add and see if it's going to give us the matrix B itself. So we'll take, first let's find B transpose. B transpose is, interchange this. So it's going to be 2 minus 4 minus 1, 3, 4, 1 minus 2 minus 3. So this is B transpose. Now we'll add this with B, with this matrix B, right? That is 2 minus 4, 1 minus 2 minus 3. If I add this, that is B plus B transpose, if I add, I'll get 4 minus 3 minus 3, minus 3, 6, 2, minus 3, 2, minus 6. Now I have to multiply with half. So I'll get half into b plus b transpose is equal to half into this. That is 2 minus 3 by 2 minus 3 by 2 minus 3 by 2, 3, 1, minus 3 by 2, 1 and minus 3. Let me call this as matrix P to make it simpler. Now I'll take the transpose of matrix P. 2, I'll get the same matrix actually, minus 3. So even after taking transpose, I got the same matrix, right? That means P transpose is equal to P. Both of these are same. So now, since P is equal to P transpose, this is a symmetric matrix. Same thing we'll do with this one, half into B minus B transpose. Let's say Q is equal to half into B minus B transpose, right? Just to make it simple, let's call this as matrix Q. So let's substitute now half, and we'll take matrix B, subtract with transpose of matrix B, right? We had obtained the transpose of matrix B earlier. We'll just copy this here. Now we'll subtract. If you subtract, what you're going to get? 2 minus 2, 0. Minus 2 plus 1 is minus 1. Minus 4 minus 1 is minus 5. Minus 1 plus 2 is 1. 3 minus 3 is 0. 4 plus 2 is 6. 1 minus 4, 5. Minus 2 minus 4 is minus 6. Minus 3 plus 3 is 0. So now we'll multiply with 1 half. So we're going to get 0 minus 1 by 2 minus 5 by 2 minus 3 and 0. This is a matrix that we are going to get. So this is nothing but we've called it as Q. Now let's take the transpose of Q. The transpose of Q is, let's interchange. So it's going to be 0, half, 5 by 2, minus half, 0, minus 3, minus 5 by 2, 3 and 0. So I have interchanged the rows and columns. Now if you notice, elements are same, just that the signs are opposite, right? Which means let's take minus outside. We're going to get minus of 0, minus half, minus 5 by 2. The signs are going to get swapped basically. So minus 3 is going to become plus 3, minus 5 by 2 is going to become 5 by 2, 3 is going to become minus 3 and 0. So now if you see, these two matrices are exactly same. This is nothing but Q, right? So Q transpose is equal to minus, which is here, and this matrix is nothing but Q. So this satisfies the condition for skew symmetric. Thereby Q is skew symmetric, because it satisfies the condition that Q transpose is equal to minus of Q. Now we have proved two things. We have proved that this portion is symmetric and this portion is skew symmetric. Now we'll have to add both the matrices and we need to get matrix B. That's when we can say that matrix B can be expressed as sum of symmetric and skew symmetric matrix. Well, let's add PQ. We call this as matrix P and this is matrix Q. Let's add both of them. This is the matrix P that we had obtained. This is a matrix Q. Now let's add both of them. When you add both of them, you will get 2 plus 0 is 2, minus 3 by 2, minus 1 by 2 is 4 by 2, which is nothing but 2, minus 2, then minus 3, so it's going to be minus 8 by 2, that is nothing but 4, 2 minus 3. So this is the matrix that we are going to get. Let's verify if this is matrix B itself. What was matrix B? This is matrix B. Now if you notice, it's the same thing. When we added matrix P and Q, we got the matrix B itself, right? We got this, which is nothing but matrix B. Therefore, we can say that matrix B can be expressed as a sum of symmetric and skew symmetric matrix. With this, we've come to the end of this particular topic. Thanks for watching. Hope this video was useful.